I want to start by saying I've never done a physics lecture off of a PowerPoint slide, so I don't know how this is going to work. But with the hurricane out in the Gulf, and we're expecting a lot of rain tomorrow and Friday, I thought I would get ahead of this and maybe record this today and offer it in case we can't meet on Friday. So we're going to start with chapter one, and we're going to talk about some basic physics, and we're going to talk about the development of radiology and how it is that we got to the point where we are now. The development from really a pretty dangerous field to a pretty safe field. So we'll start with the nature of our surroundings, and just basic observation. If you look around, everything is made up of either matter or energy, or matter that is utilizing energy. So a combination thereof. So matter is anything that occupies space. It has mass. It's made up of atoms, and atoms are just individual little bitty parts of specific elements that come together to create something larger than itself. Um, we have a tendency to equate mass with weight. It's not really the same thing. Weight is the effect of gravity on a mass. So you can't really have a mass without weight providing you're in a gravitational field, but it's not necessarily the same thing. So weight is going to be different according to gravitational pull. So I'm going to open this link here. The link wouldn't open in exactly the same window that I would like for it to have opened in, but we can certainly take a look at the information that I wanted you to see. So weight being the effects of gravity on mass, weight can vary. And the textbook mentions the moon, and we'll talk about that here in a minute. But the effects of gravity or gravitational pull on objects is going to be different in different atmospheres. For example, if you were to travel to Jupiter, your weight would be 2.53 times the your weight here on Earth. So gravitational pull is 2.53 times greater on Jupiter than what it is here on the Earth. Gravitational pull on Neptune is slightly higher, but it's not as significant as what it is on Jupiter. So the gravitational pull on Neptune would make you feel, if you weighed 100 pounds, you would suddenly gain 12 pounds. Saturn would even be less significant. And then once we get down to the gravitational pull of the gravitational pull on the moon is 1/6 of what it is here on the Earth. So by traveling to different planets, you don't necessarily gain or lose mass. You might after a while, but that's a little bit deeper of a topic than what we need right now. But you don't necessarily add or decrease mass. What you add or decrease is weight due to the gravitational pull from those particular planets. So a measure of mass is kilogram. Weight is measured in a lot of different other ways. We can measure weight in pounds. We can measure weight in stone. But weight and mass are not necessarily the same thing. For example, if you took a quantity of water and you froze it, and then you put that frozen water, which is ice, inside of a glass with other water, then what you observe is that the water floats. The frozen water floats. So the ice floats. What that tells us is that ice has the same mass. You have the same quantity of water molecules that you had before you froze it, but what happens is it gets lighter. So you have the same mass but different weight. And then if you were to put all that water on a hot plate and melt it and eventually turn it into water vapor, the individual water molecules don't change. They become water vapor, but it's still water. Fundamentally, it's still water. So if you could gather all those back together, you would have the same mass, but it becomes water vapor and it can actually float. So three different states that water can be in: water, vapor, ice, all have the same mass but totally different weight. Another way to look at it is if you had a quantity of a solid substance like aluminum versus lead. So if you had a bar of aluminum that was maybe 4 inches by 4 inches by a foot long, it's going to weigh totally different than a bar of lead um, of the same size. And that is because of the elemental weight of those two things are going to be different because the mass is different, but the chemical makeup is different. So the mass, the overall area between the two are the same, but the effects of gravity on the two are completely different. The aluminum is going to be significantly lighter than the lead. So nature of our surroundings, um, energy. Energy is just defined as the ability to do work. Matter uses energy. There is a energy equivalent of mass. And we can see that at work if you were to take a tree and cut the tree down and burn the tree, what you would get is heat off of the tree. That's a basis for Einstein's theory of relativity, E equals mc squared. The energy of an object is equal to the mass of the object times the constant. The constant is the speed of light squared. So everything in the universe is matter or energy or some combination thereof. You are matter that uses energy. You eat food, it is processed into energy that you can utilize, and some of that, unfortunately, once your growth plates heal up or seal up, the only growth that you get at that point is soft tissue. But if you overeat, then it becomes that energy is again transferred back into mass. So you can convert mass to energy, energy to mass. So energy, there's a lot of different types of energy. The first one that we're going to deal with is potential energy, and that is energy of position. It's unrealized energy. It might not be active energy, but it's stored energy. So it's a potential to do work by its position. Once we release that stored energy, it becomes something totally different. It becomes realized energy at that point. We'll get back to that. Kinetic energy is the energy of motion. It is the released potential energy. This is a little video I like to show that shows the difference between potential and kinetic energy. So I'm going to back it up and we're going to talk about this. So I said that potential energy is energy of position, or stored energy. And it can be stored, it doesn't necessarily have to be position like utilizing gravity, but it is stored energy, is energy that's not been realized yet. So what we have in the mousetrap is we've got this spring that's coiled, and it's stretched to the point where you've got some resistance on it. So it's in an unnatural state. So we're not utilizing gravity here. What we're utilizing is a spring essentially. So we've pulled this thing back, this basic mousetrap. You pull this thing back and you put the, I won't say safety, but the mechanism that holds the spring back into place until the bait stick over here is disturbed. And then that spring, the natural position for this is to be over here until the again the bait stick is disturbed, and once you pull this mesh, so the natural position for the spring to be over here, if you pull it back, you increase the tension, you increase the potential difference or the potential energy, so that whenever the trap is sprung, the spring flips back over to the other side and it catches whatever's in the way of it. So we've got potential energy. Once the trap is sprung, snap, we've had the kinetic energy as the spring moved back over to its natural position. The massive rat pulls it back and sticks the coyote's tail into it. So we had potential energy followed by kinetic energy converted twice there. Now we're compressing a different spring and we create potential energy, but the coyote is holding the spring compressed, still potential. He lifts his feet, friction is gone, and he's got kinetic energy. Doesn't work out so well for him. We still have kinetic energy. Now we've got not only kinetic energy coming into play, but we've got kinetic energy created by the gravity. So truly we have energy of position here. He's hanging over the edge of the cliff. Gravitational pull is going to pull him downward. Now the spring is about to be stretched. So his kinetic energy. Now, since the spring is stretched completely, again we have potential energy until the rock starts to move. Kinetic. And it's done. So kinetic energy is the energy of motion. The potential is released. Then we have chemical energy. And chemical energy is the energy released because of a chemical reaction. So you mix bases and solids together, and sometimes you'll get an explosion. That's chemical release or chemical energy. If you eat, then your body digests the food and it converts it to energy. So food to energy. Chemical explosions, if you mix certain chemicals together, just like bases and solids, you'll get an explosion. The textbook mentions dynamite is certainly an example of chemical reaction that causes an explosion and therefore chemical energy. But where we most often see it and where you can see it is in your telephone. You have batteries, so you've got chemistry inside of the battery that creates an electric flow. So what we've got there is chemical energy creating something else. In this case, it's energy for your brain and for your body. Here, bases to solids, you're probably going to create, some sort of explosion or some sort of release of gas. Chemical explosion, certainly you're going to create heat, and then batteries, you're going to create electricity in most cases. So electrical energy, we have movement of electrons, and we talked about that today in class. What we have is movement of electrons through a circuit. And for the reasons we discussed in class today, they're all about negative charges. The nucleus of the atom, whenever we create electricity, doesn't move. The electrons being in the outer shells outside of the nucleus of the atom are free to move. And if we add a supply of electrons, then what that does is it just pushes electron through the conductor and we get electric flow, and that would be electrical energy. Most things, most different types of energy and energy use create thermal energy. That's just heat. So we refer to that as kinetic energy at the molecular level or molecular kinetic energy, and we measure that in Celsius or Fahrenheit, Kelvin, and a couple other means of measurement. So the more motion you have, the more heat you're going to have. So electrical energy, that's how your toaster works. What we get is a flow of electrons through a circuit that creates a significant amount of heat, and you put your toast or your bread inside of the toaster, you run the electricity through it, and it toasts your bread because it gets hot. So electrical energy creates heat. Nuclear energy is energy contained within the nucleus of the atom, and it can both be very good in creation of electric energy, or it can be very bad in creation of atomic explosions. Then electromagnetic energy is anything that behaves in a lot of ways like light. So that's what we're going to be studying for much of this semester, but it includes radio waves, microwaves, light, infrared radiation, X-rays, gamma rays. So there's a lot of different types of electromagnetic energy, and it exists on a spectrum from low energy to high energy and from long wavelength to short wavelength. And we'll talk about those, what those mean later in the semester. But the reason we call it electromagnetic energy is because it demonstrates both an electric and a magnetic property. All levels of electromagnetic energy demonstrate both of those properties, both electric and magnetic. So energy and matter are interchangeable. Matter can use energy, matter can create energy, and vice versa. Energy can create matter. Energy and matter can be transformed from one type to another. Energy can consume matter, consume food, and it creates energy. You consume too much and you get fat. So why is all this important? I'm going to go back up to that graphic here in a minute, but we're going to use every one of these in imaging, in creation of X-ray. So we need a source of electricity. So in lecture today, I used nuclear power plants as a possible way to get electrical energy. So what we're going to do is we're going to get electricity from nuclear power plant. So we've got nuclear power plant creating electrical energy. The electrical energy that we're going to use, if you remember again from today's lecture, we're going to take that electric energy and we're going to transform it. We're not really going to generate it in the X-ray system, but we can transform it from low energy to high energy. So when we create that high energy, that high kVp, what we're actually creating there is a high potential difference, a high electric potential in the X-ray tube. So until we make our exposure, all we have is potential energy. When we apply the kVp, then we release the electrons and they become kinetic energy. They travel across the X-ray tube and they slam into the anode at a very high rate of speed, again, somewhere between a third to a half of the speed of light, and they are transformed into electromagnetic energy. The type that we want is X-rays, but unfortunately we get most of that being heat. So Nuclear energy becomes electrical energy becomes potential energy becomes kinetic energy becomes electromagnetic energy. Unfortunately, most of what we create is heat. It seems like what we left out was chemical, and we don't necessarily need to know about chemical, and that would be untrue because chemical energy we're going to use in our portable units. They're battery powered, so we will be using chemical energy as well. So running back through it, we use all different types. Chemical or nuclear energy can create our electrical energy. Electrical energy is manipulated to create high potential difference or a high electric potential. We release that and it becomes kinetic energy to travel across the X-ray tube. The electric energy is used to create a magnetic field to turn the rotor, also the thing that spins in the X-ray tube that I passed around today. And that also results in kinetic energy. And what it results in most of the time is heat. That is thermal energy. We create a little bit of light, but we also create just a few X-ray photons out of that, proportionally just a few. So how we create the X-rays, again, is the electrons are slowed. And in the slowing of the electrons, we lose that kinetic energy and we get a creation of X-ray photons in Bremsstrahlung X-ray creation, and that again is the electromagnetic radiation that we're most interested in. The visible light is also electromagnetic radiation, as is the heat, the infrared radiation that's coming off of the filament and eventually the entire tube. But the main type that we're going to be interested in is the X-rays. Where else we use visible light is half of you have been through lab. Hopefully the rest of you can get through on Friday if the weather's not bad, too bad. But the light that you see coming out of the X-ray tube, seemingly out of the X-ray tube, is not really out of the X-ray tube. That's out of the apparatus below the X-ray tube, and that's what we call the collimator housing. And a collimator housing has a light bulb inside of it that shines and reflects what should be the radiation field, but it's not truly a radiation field. You don't get the radiation field until you make your exposure. So radiation, again, is kind of a scary word, but it's not all that scary. All it means is movement of energy through space. Not all of it's harmful. As long as you don't get to too high of a level. Heat is transference of heat from one place to another is a form of radiation. So unless you stand too close to the source of the heat, it's not going to hurt you. It'll actually help you. Sound is a type of radiation, and or the movement of sound is a type of radiation, and it's non-harmful unless it gets too loud. Electromagnetic radiation, again, demonstrates both electric and magnetic properties, and it behaves in a lot of ways like light. X-rays don't really travel or don't really behave entirely like light, but they share some of the characteristics. So it travels in waves, it travels at the same speed, and that would be the speed of light. So, and that is your constant. And mc squared equals mc squared. The c is actually speed of light squared. So it travels at speed of light and it exhibits both electric and magnetic properties. It behaves like light in a lot of ways and it travels in waves. So if you look in your textbook and if you're using a previous edition, the reference here, figure 3-6, is not going to be the same in your textbook, but you can find it in the textbook. What it looks like is a blue background with a lot of squiggly lines running through it. So in my textbook, it's on page 49. So what that represents are the different types of electromagnetic radiation. That may not be comprehensive, but it shows you the energy levels that we're talking about. So what you'll see and what we'll talk about in chapter 3 in a few weeks is how energy, frequency, and wavelength of the different types of electromagnetic radiation determine the the type and the energy level of the type of radiation. So ionizing radiation is what we're most interested in for this class. An ion is a charged particle. So if you think about your subatomic particles, what you've got are protons, neutrons, and electrons. Protons and electrons are charged particles. So if you separate um, and you have a dissimilar number of protons and electrons, then what you're going to have is an ion. All right, so you've got protons with a positive charge, electrons with a negative charge. They're opposite charges, but they're equal. So if you have a proton and an electron together, what you've got is a neutral charge. If you remove the electron from the proton, now you've got two different things that are ionized. You've got the positive charge all by itself and the negative charge all by itself. So those are ions. Ionizing radiation is radiation that is capable of removing an orbital electron. So if we have a high enough level of radiation, energy of radiation, it can pop an electron out of the orbit of an atom. And in doing so, the electron becomes a free radical and it is not bound to anything. So it's an ion. But if it removed the electron from an atom, the atom then becomes ionized as well. Because it lost a negative charge, now it becomes positive. So what you've done is you've made two ions. With ionizing radiation, if you have a interaction that removes an outer shell electron and that atom does not attract an outer shell or some other electron, then what you've got is an ion in the atom itself. So it creates two atoms. Two of anything, you got two shoes, we call that a pair of shoes. So what you've got once you ionize an atom is an ion pair. So it's a pair of charged particles. So being irradiated just means that you've intercepted ionizing radiation. You probably become ionized. So it looks something like this. We've got radiation coming in, and whenever I draw on the board, if I make a squiggly line, that's supposed to be representative of electromagnetic radiation. So if I'm drawing and I draw a straight line with an electron, that means that what I'm drawing is what we call a projectile electron. It's an electron that's traveling eventually to make contact, in most cases, with the anode and create an X-ray photon. But the squiggly line I draw away from the atom, that's supposed to be representative of ionizing radiation. So what I drew in class today is not what you're looking at here. This is the X-ray photon after it's being created, hitting a target atom inside of the patient. If it removes an electron, then you've got an ion here. This is also an ion, and those two are ion pairs. So we receive ionizing radiation from a lot of different places. And we talked about some of these in class today as well. So really, fundamentally, there's two. There's natural, environmental, that's one category, and then there's man-made. So it's either natural radiation or an unnatural radiation. So where we get natural radiation is from space, being one. So we get radiation from the sun, we get X-rays from the sun, we get X-rays from the stars. So those will be cosmic rays. But we also get terrestrial radiation. And terrestrial radiation, the main contributor to terrestrial radiation is radon. But you also get radioactive breakdown from things like plutonium, other radioactive substances. But you also have those deposited internally. So you've got some radioactivity going on inside of you. You're being ionized by your own body. in some cases. Carbon-14 is an example. Carbon-14 exists inside of your body, and you're going to have a constant rate of carbon-14 as long as you're alive. Once you die, your body starts to decay, and that carbon-14 starts to decay. You don't continue to replenish it, it starts to decay. And that's the basis for radiocarbon dating, is that they know within a given variance how much carbon-14 you should have inside of your body at the time of your death, and it decays at a continuous rate, a predictable rate, so they can tell how long within years, how long an organism has been dead, essentially, by carbon dating. The others are man-made. So we got non-man-made, we got man-made, we got natural, we got unnatural sources of ionizing radiation. The main contributor to man-made is going to be medical. So X-rays, CAT scan, nuclear medicine, bone densitometry, all of those will be medical applications. Industrial radiography would be things like they'll use radioisotopes in some cases to determine the integrity of welds. So sometimes they'll use them on airplanes to see whether or not they've got cracks in the wings, whether or not they got cracks in welds, things like that. Pipelines, they'll use sometimes radioactivity to determine whether or not there's cracks in the welds in pipelines. Consumer products, believe it or not, smoke detectors have small pieces of radioactive substances inside of them. And then we get some from nuclear power, nuclear fallout, those sort of things. So that just runs through everything that I just mentioned. All right, so it's just kind of goofy. Discovery versus invention. Discovery is sometimes accidental, as opposed to invention is not. Invention is generally you set out to try to create something, as opposed to discovery is something that you observe, sometimes totally by accident. The reason I bring this up is because X-rays were discovered, man-made X-rays were discovered. All X-rays were discovered fundamentally. The equipment that enabled X-ray creation was created. Okay, so there you had inventions, but the actual discovery of X-rays was quite accidental. And it was made by a guy named William Conrad Roentgen. And what he was doing was he was experimenting with cathode rays. So what they were looking at, and a lot of people were experimenting, and he just happened to be the one who either noticed the phenomena or identified it, one of the two. But they weren't really looking for X-rays. What they were trying to understand and get a true understanding of were the behavior of electrons inside of cathode ray tubes. What they were using was what we call a Crookes tube. And a Crookes tube is not a vacuum tube like a light bulb. It's a partially evacuated tube. And it's important that you understand it's partially evacuated because the development of X-rays as a safer means of treating patients and making diagnoses was that we needed a better X-ray tube, and we eventually came to the point where it was realized that a partially evacuated tube was inadequate and had become truly a vacuum tube. We needed a vacuum tube. So this is a video that I wanted to show you. It is a Crookes tube, and just to give you some sort of idea of what it is that they were experimenting with at the time that Rinkin discovered X-rays is they had a tube sort of like this. And what we have in this tube is we have a connection with the source of electricity going to it, so that whenever we supplied electricity to it, the end of the tube has this substance that the electrons would interact with, and we would get this glow, or they would get this glow. So what they were doing is they were trying to see how it was that electrons behaved in different environments. So you'll see him, there we go. You'll see him fold this thing down, or point this thing down, so that this cross would be within the stream of electrons. So once he turned the thing back on with that in a way, what he saw was this cross, what they call a Maltese cross. It blocked some of the electrons, so you saw the shadow of the cross on the end of the X-ray, or on the end of the Crookes tube. When he turned it off, obviously it went away. Now, I'm going to try to fast forward this until we get to where they realize that electrons have magnetic properties. So he's going to take a magnet. It's a magnet. He's going to get it close to the stream of electrons, and you can see the distortion. You can see the cross isn't moving, but you can see the distortion of the image. So what we know about charges is, in the atoms and with charges on magnets, is opposites attract and like charges repel. So what you'll see is that when the magnet is pointed in a particular direction, you get a certain degree of distortion, and whenever they reorient the magnet in the opposite direction, the distortion completely changes. So this is what they were trying to learn. They were trying to understand the behavior of electrons in different environments and the effects of things like magnets on electrons, and they just didn't really understand what electrons or electricity itself was. So what Rinkin did was he took his Crookes tube and he just wanted to see if he changed the variables a little bit, and he completely covered this thing with photographic paper, black photographic paper, so no light could get out. He was curious as to whether or not he could determine what the electrons were doing inside of the tube without his observation. So he covered it up completely, and then he powered the Crookes tube back on, and once he powered it back on without any light coming from the Crookes tube itself, what he observed was a plate across the room would start to glow. He didn't understand what was going on. He didn't know that anything was coming out of the tube except for the light he could visually see, but when he turned the tube back off, the plate would stop its glow. When he turned it back on, it would start to glow again. So clearly what he had was something that he could not see, but yet it was penetrating not only through the glass, but also through the paper, traveling across the room, interacting with this substance that's on this plate. And the substance is what we call barium platinocyanide, and it would glow whenever the tube was energized. So he said to himself, I got something going on here. I don't know what this is, but I got something going on. It's a form of light, but I can't see it and I don't understand it. X is the scientific unit of the unknown, so he didn't know what it was, but he felt like it behaved like light, so he called it X-light, and X-light eventually became X-rays. So Rankin locked himself in his laboratory for a couple of weeks, and he studied the X-rays extensively and wrote a paper that eventually became his foundation for a Nobel Prize in Physics. But during his experimentation, he decided he would try to see what would happen if he put human anatomy inside of the beam of this invisible light. And what he did was he took an image of his wife's hand, and she exclaimed whenever she saw the image that she had seen her own death. Now, this image, it's ugly. The resolution is very, very poor, but you can clearly see the bones, and this thing is a ring. So the interesting thing here is I don't think cubic zirconium was a thing in 1895, but we can conclude that this thing is not a diamond. And I tell you that because I know it's not a diamond because you can't see through it very well. You can't see through it at all on this image. So you notice that you can see through the bones, especially the thinner portion of the bones. It gets a little dicey up in here, but you can't see through this at all. This looks like a solid piece of metal, and it probably is. But if you consider what a diamond is, that is compressed carbon, and you think of what we are, and that is carbon-based substance, then you realize that X-rays will penetrate carbon fairly easily, and nothing's getting through that. So either this is solid metal or it was a fake diamond ring, one of the two. I would think probably solid metal. So he got the Nobel Prize. He called it X-Light, and most of what he teaches or what he studied and observed and based his paper on that became his Nobel Prize are what we teach still in X-ray school today. So where did it go from there? So we got X-rays. We know X-rays can penetrate things. We know X-rays can penetrate through human anatomy. So what are we going to do with it? We can create diagnostic X-rays. We can create fluoroscopy. We can make diagnoses. Eventually, we got to the point where we could treat cancer as well. And I say eventually, but it really didn't take all that long before they started treating cancer with it. So we can do all this stuff, so we're good to go, right? Well, no, is the answer. Radiation burns were common. As a matter of fact, Thomas Edison's lab assistant, one of his very close friends, as his lab assistant, died from radiation exposure. So what we have here in this image is the first, suspected the first medical X-ray exam. So this guy here, he's a good-sized kid, but he's, I think it was described as maybe a 12-year-old boy who fell and broke his arm. So they wanted to know if they could make a diagnosis and take a look at the bones and see whether or not it is broken. So this is X-ray tube, and notice there's nothing on this X-ray tube. It's glowing just like a light bulb would, but it's creating X-rays as well. And it took maybe a half an hour to make the exposure. If you've had an X-ray of your arm, it takes fractions of a second to make a good X-ray of an arm. So if it took 30 minutes to make an exposure on this poor kid's arm, it was a tremendous amount of radiation skin dose that the patient was taking. We never energize the X-ray tube without it being inside of what we call the protective housing, which the protective housing and the collimator housing together reduce the radiation dose to the patient. So it's just unsafe. And if you notice, these guys are staying in the room with the patient. Most times when you make an exposure, radiation exposure, you're going to be behind the wall to protect yourself from the radiation. They just didn't know what they were doing yet. So we had to learn to reduce the dose. And we did that in a lot of different ways. We developed better generators. Snook's generator was invented in 1907. The X-ray tube was improved. We started using a Coolidge tube, which we use variations of it, but we've changed it over the years. But it's a vacuum tube. The significance of that is not necessarily that it lowers radiation exposure, but it gives us more consistent exposure so we know what we're going to get. The problem with a semi-evacuated tube is that there's still gas inside of the tube. And with the gas inside of the tube, what we get is erratic exposures. So we don't know if we're going to get a good X-ray or not. As opposed to a vacuum tube, we don't have those erratic exposures, and we can pretty much count on our technique giving us a good X-ray, providing we set the correct KVP and mass. So intensifying screens. Intensifying screens are showed on Monday. If you weren't in class on Monday, I'll try to remember to show on Wednesday. But intensifying screens were a way of, instead of using X-ray to create the image, what we used was the light coming off of the intensifying screens in order to accomplish the same thing. But this is basically what an intensifying screen is. An intensifying screen is inside of a rigid cassette. And we have the intensifying screen inside the cassette, and we put a film inside of the cassette with an intensifying screen. And what happens is that whenever we make an exposure on the intensifying screen, just like the plate that Rinkin observed glowing across the room, when X-rays interact with the intensifying screen, then what it does is glows. So if we have this inside of a cassette, and it's dark inside of the cassette, the film doesn't get exposed. You know, if we put the patient's anatomy on top of that thing, this whole cassette, we make an exposure on it, then the X-rays penetrate through the patient's body and they expose the film. But they also hit the intensifying screen, which glows in response to the X-ray stimulation. So it intensifies the image, and that's why we call it intensifying screen. So I'm going to play this real quick, and what you're going to see is once he makes the radiation exposure, once he makes X-ray exposure, this thing's going to glow green. So what you see is the glow of the screen, but he's got something on collimator housing that blocks X-rays. So if it looks like maybe a washer or something like that on the tube housing. So it casts that right there. So if we had a patient's anatomy with a fracture, what we should be able to see is we should be able to see the bones, and we should be able to see any kind of abnormality. So when we implemented and started using the intensifying screens, most of the exposure to the patient was reduced significantly. So we don't use intensifying screens in film anymore, but just to give you some sort of idea of how much it reduced the exposure. Most of our screens and films, the combination of screens and films were measured in speed. Like 400 speed is what we used for chest X-ray. And that 400 represented basically how much intensification of the X-ray, how much intensified the signal was to the film because of the intensifying screen. So I stumbled through that, but basically what it means is that our radiation exposure, we could use 1/400th the amount of radiation to make the same exposure with the intensifying screen versus without. The slowest speed screens, the screens that glowed least, were still 200 speed. So what that means is for this kid, where we had this X-ray created, wherever he went, there we go, is if this took 30 minutes to make an exposure for this, then we could cut that time down by a factor of 200. Significant radiation dose reduction. Now, the dose reduction was not that significant to begin with. We only had one screen and bad film. The 200 and 400 speed reduction was overdevelopment. It was over time. It became that efficient at reducing radiation dose. So what we had, again, in this example was one screen, one film. Somebody else came along and they said, well, you know what, we cut down radiation exposure to the patient by using one film. What if we put the film in between two of these plates and we put the stuff that puts the image on the plate or on the film on both sides of the film? So what they did was they took X-ray film, and instead of having the emulsion, which is the goo that records the image, instead of having the emulsion on just one side, they put emulsion on both sides, used an intensifying screen on both sides. And so what it effectively did was we use exactly half the radiation dose, because it was as if we took two images and stacked them directly on top of each other. So double emulsion film with two intensifying screens cut the dose back again. A dentist by the name of William Rollins implemented a couple of things, and those things were filtration and beam restriction. So again, I'm going to go back to this image. So we've got an X-ray tube here, and every X-ray that's coming out of this is going off in pretty much every direction, including directly down to this poor kid. So some of those X-ray photons, if you remember from the lecture today, we can create X-ray photons in pretty much every energy level, and very briefly touched on and used the example of a meteorite coming close to the Earth. If it comes close to the Earth and the Earth changes its trajectory, then it, in the analogy that I was using and changing that to X-rays creation and the electron getting close to the nucleus of the atom, we lose a lot of energy. And with the loss of a lot of energy, we create an X-ray photon that's very high energy. But if it doesn't lose much energy, then we create very low energy X-ray photons that have no chance of getting through the patient. So a lot of the X-rays that are coming out of this are very low energy photons that are never going to make it through the patient. So they just hit the patient's skin and they absorb into the patient. That's what we call entrance skin exposure. The reason that X-ray exposure in the very early years of X-ray creation and development into medicine was so dangerous was because of entrance skin exposure. Radiation exposure to the patient, high radiation exposure to the patient, looks a lot like a sunburn. So we were getting radiation burns, a lot of radiation burns, because these low energy photons had nothing except skin exposure. So Rollins came along and he decided that if he removed those low energy photons, what he would be left with is a higher average energy X-ray beam that would add less to the patient exposure. And he called that filtration. The other thing that he figured out was that if I'm making an exposure to the patient's arm, I don't need to expose the entire room. So he created beam limitation. So beam limitation and filtration were two things that were implemented strictly for patient care, to limit the amount of radiation that the patient receives from the X-ray tube. So all of these other things limited patients' exposure by reducing the amount of mass that we needed, but these two were just for radiation exposure, given the amount of mass the patient was already going to receive. So it cut down on radiation exposure. So Intensifying screens, I explained that. Double emulsion films, I explained that. These two really go together. The significance of filtration is it removes those low energy photons so that we get a higher average energy, and it removes the X-ray photons that would just not make it through the patient anyway. So the better generators enabled us to use a higher KVP. From the lecture today, if you remember KVP and the lecture about the discussion rather about the meme, the KVP is the power of the X-ray beam. And it's the penetration. KVP controls penetration. Potential difference controls penetration. So if we make an X-ray beam that's more capable of penetrating, then what we can do is we can make an image with more efficiency than this. So even though we can see through the fingers, we really can't see through the fingers very well. If we had a gross fracture, certainly we could see that if it was totally displaced, but it's kind of tough to see through a portion of the fingers. So with a higher KVP, we can see through more structures. This amount of exposure would do nothing for penetration of the abdomen, let's say. So the better quality generators enabled us to increase KVP so that we could see more stuff. With increased KVP, we can also reduce mass and save patient exposure. We can make X-rays of other body types that a very low energy photon or a very low energy X-ray machine would not be able to. So in all of these, anything that reduces the amount of radiation we use, and the amount of radiation that we use is just measured in mass. That is the number of photons that we create based on the number of electrons that we send across the tube, which is based on the mass that we use. Anything that reduces that amount reduces radiation dose. So I'm going to talk about some things that are a little bit probably advanced for now, but some things that you need to be familiar with, some terminology that you're going to hear for the next 2 years. So contrast and density. Contrast is, all contrast means is difference. So the difference between this area and this area. In X-rays, it's a difference between dark areas and light areas. So that's contrast. Difference is all it means. We have to have contrast in order to visualize an image. So if all this entire image looked like this up here, then we wouldn't be able to see the fingers at all. So if this entire thing looked like that, we wouldn't be able to see the fingers. So we'd have no contrast and would be unable to make any kind of diagnosis. At the same time, density is important. So we got contrast being difference, and density is just darkening. So when we're looking at this image, when we're talking about radiographic density, and what you'll learn is there are different types of density. There's patient density, subject density, radiographic density. In radiographic density, we're talking about overall darkening of the image. So the density on the finger is less than the density in the soft tissue. Okay, so we got dark image, light image. So increased density, decreased density. Increased density because we're in between the fingers, decreased density. Up here on her knuckles, and I kind of wonder if maybe Bill's wife might not have had some rheumatoid arthritis going on. The proximal ends of these portions of the bones and distal end of these portions of the bones shouldn't really be that dark. But we've got an increased density here, decreased density here and here. So dark means increased density, light means decreased density. The difference between those two would be your contrast. And we have to have both in order to make a quality X-ray image. So that contrast generally suffers with a safer X-ray beam. And that doesn't really apply to beam restriction, but the things like increased KVP usually makes contrast worse, makes things more gray. If you remember in the discussion of technique and grids versus ribs versus chest X-rays today, I said that if we wanted to see ribs, we want to decrease KVP so that the x-rays stop on the ribs more. That would give us a higher contrast, as opposed to the increased KVP gives us a lower contrast because we get more penetration. So generally, whatever makes the x-ray safer destroys contrast until we get to beam restriction, and beam restriction in grids actually increase contrast. Grids, on the other hand, do not improve or reduce patient dose. Grids eliminate some of the unwanted remnant x-rays that come through the patient. These are remnant x-rays or secondary radiation that passes through the patient. It was developed by Gustav Bucke, that's on page 10, and it is designed to absorb scatter radiation, and unfortunately it increases patient dose dramatically. And by dramatically, I mean anywhere from 3 to 6 times. If you were to take an image without a grid versus an image with a grid, once you introduce the grid, you're going to have to increase your mass by a factor of 3 to 5 times what it was before. Now, that seems pretty extreme until you go back to the discussion earlier, where we're talking about the radiation dose being cut back by a factor of 200 to 400 times. So all of these things, with the exception of the grid, improved efficiency of x-rays, and creation of x-rays and exposure to x-rays, and made it much safer. Grids kind of reverse that a little bit, but it's still significantly safer with a grid than what it was without a grid 100 years ago. So our radiation dose to the patient, radiation dose to the public, and to technologists has gone down very dramatically, making it much safer. Still, though, you want to protect yourself. So basic radiation protection for the patient is we want to keep our radiation dose to the patient as low as reasonably achievable. So that's a concept we call ALARA, A-L-A-R-A, ALARA, keep the radiation dose as low as reasonably achievable. So how we do that is we limit the initial radiation exposure to the patient by using proper techniques. So it's important to eventually learn your KVP and mass. For right now, most of the exposures that you're going to make in the department are you're going to have to select a KVP or an exam type that'll give you an automatic KVP, but your mass is generally taken care of on the exposure through what we call automatic exposure control. We'll talk about how that works later in the semester. But we want to use a well-filtered beam, and that's already built into the protective housing. And we certainly want to limit the beam to the anatomy of interest, and that is the collimation that we've talked about, or we did talk about Monday in class. So that's beam restriction. You only want to expose the portion of the patient that you need to expose in order to make your x-ray. The other things that you can do to reduce patient dose would be to shield the patient. If you're taking an exposure that's going to be a large exposure, you may want to shield not only the patient, but also to make a better image, you might want to do something like lay a lead shield behind the patient if you're shooting like a lateral lumbar spine to absorb some of the x-rays so that they don't unnecessarily interact with the image receptor. It's not really patient protection, but that is image improvement. So provide shielding, use protective barriers. If somebody else has to be in the room, use protective barriers, limit the number of repeats. Make sure that you communicate with the patient, tell the patient what your expectations are so that they're not moving. Motion is a big reason for repeats. So that's radiation protection for the patient. Radiation protection for everybody else, including you, is to spend as little time around the x-ray beam as possible, stand as far away from the energized field as possible, and shield whenever you can. If you need to be in the room with a patient, anytime you're in the room when the x-ray beam is on, and you will have to be, then you need to wear your appropriate shielding in the form of a lead apron, thyroid shield if you so choose. But time, distance, and shielding is your radiation protection and radiation protection for the general public, as opposed to ALARA being the radiation protection for patients.